are going to start with probably the last topic. It's about forced convection mass transfer. Now, we already have an idea of what is mass transfer, the different ways by which mass can get transferred across a liquid, solid or a gas. The principal components are diffusion and flow. The common example of mass transfer takes place in situations where you have both flow and diffusion. So, what we are going to look in today's class is a problem which is a coupled problem, coupled with fluid flow and mass transfer. So, it's the title of today's talk, today's lecture is Diffusion into a Falling Film, but essentially this is forced convection mass transfer. So, in order to analyze such a system, the example that we have chosen is, suppose we have a vertical wall and along the vertical wall some liquid is draining. So, the liquid is falling along that vertical wall with some predetermined velocity. Now, you have analyzed this problem in fluid flow. When a liquid falls along a vertical plate, you have solved the problem for an inclined plate, but that same analysis can very well be extended to vertical plate by changing the angle beta. If you remember the first problem which we have done in transport process 1, that was for fluid flow in a film form across, or rather along, an inclined plate. And we have done by shell momentum balance what would be the velocity profile, and we have seen that the maximum of the velocity will lie at which point? On the solid surface or at the top of the liquid film. So, at the top of the liquid film, and we could express the velocity distribution inside the liquid film as a function of whatever be the velocity with which the top layer of the liquid is moving, a distance of any point from the top, the gravitational forces acting on it, and so on. Now, we are assuming such a system for our mass transfer studies, but instead this time the plate is vertical. So, the liquid will be falling along the vertical plate, the maximum will be at the liquid gas interface, and on the solid liquid at the solid liquid interface the velocity would be obviously 0 due to no slip condition. Now, such a system, let us say, is now exposed to a gas environment. So, the film on the other side, on the free side, is in contact with a gas which gets absorbed in the liquid. So, what I have drawn here is a schematic of such a process. The dashed line of width W and length L is the solid plate, and I have a liquid film which is falling along one side of the solid. So, this is my liquid, that is the solid, and on this side I have a gas. The gas molecules are getting absorbed at the liquid gas interface. Width W, length L, that is the coordinate system x, y, z, and let us say this film has a thickness equal to delta. The thickness of the liquid film is delta. Now, what is going to happen to the gas molecule which gets absorbed at the liquid gas interface? That specific molecule which is absorbed, the liquid film starts as pure liquid. So, the implication of pure liquid is that no gas molecules are present in the falling film of liquid at z equal to 0. And when it comes to at z equal to L, it is obviously going to contain some amount of gas which is absorbed in it. So, when the first gas molecule gets absorbed at the top or near the top of the liquid film, the gas will move in plus x direction or in plus z direction. This gas molecule, when it gets absorbed at the liquid gas interface, would it move in the x direction or z direction? Okay. I heard Z and X. Why Z?
The liquid is moving.
Okay. So, the flow of the liquid will try to take the gas molecule with it in the z direction in yx. There is no concentration of the gas inside the liquid. So, as a result of which the liquid I mean the absorbed gas molecule will travel in the x direction as well. So, any molecule of gas absorbed in the liquid will try to move in the x as well as in the z direction. Now, if we think about a little bit more, can there be flow in the x direction? Can the flow of G in the x direction be affected by diffusion? I will assume it is one dimensional flow. So, that means the flow of the liquid is only in the z direction, but a gas molecule at this point, when it starts to travel in this direction, is there a possibility that it may drag some liquid molecules with it, thereby causing somewhat a two dimensional flow in this direction? Before you say no, is it an unqualified no, or you want to qualify your statement with some restriction? How?
Density of the liquid will be much higher than the gas.
Okay.
The momentum transfer by the gas to the liquid.
All right. So, what he is saying is that the mass of the gas molecules will probably be small compared to that of the liquid. So, the possibility of the gas molecules inducing a flow in the liquid in the plus x direction is rather small. Is there a situation where is this also like a general statement, or would you want to add one more rider to it? Suppose this is ammonia and this is water. What is going to happen? Okay. So, if the solubility of the gas molecule is very high, then there is a possibility that such a system may generate, such a situation may form in which there would be a flow in the plus x direction. So, right now the first restriction that we are putting on our system is that the gas is sparingly soluble in the liquid, as a result of which the principal flow in the x direction is due to diffusion, whereas the flow in the z direction is due to bulk flow. Can there be diffusive flow in the z direction? Why not? Why no? See, think of, let's say I am blowing this section up. So, I have 3 gas molecules at a lower z, 2 gas molecules here, the flow is in this direction. I am sorry, it should be 4 and so on. So, would there be a diffusive flow as well? The concentration gradient is in this direction. Okay, the flow is in this and the other direction. Again, as we have expressed that the gas is sparingly soluble, the major flow of that dissolved gas in the z direction is going to be governed by the bulk flow, not by the diffusive flow. Okay. So, those are the two situations which we have to keep in mind while formulating this solution. What I am saying, repeating the last point I have mentioned, at the top, near the top, the penetration of the gas molecules, let us say only 3 molecules have penetrated.
They will be symmetrical. For the gas molecule doesn't know at what height or at what value Z is increasing.
All right. What he is saying that, let us say at this is Z equal to 1 unit, 1 millimeter, and this is at Z equal to 5 millimeter. All right. At Z equal to 5 millimeter, if you take the average concentration at a fixed Z, would this average concentration be more compared to that of 1 millimeter? Should it be same? So, if it is same, then I do not need this part of the film at all. I just exposed only a small part, only a small cross section, small delta Z of the film, and the amount of gas picked up by that small delta Z layer of fluid would remain unchanged. So, in such an contacting device, the length is unimportant. don't you think that if the length is more, then more gas molecules will be absorbed by the liquid?
So per unit length will remain same.
Let's okay, you are saying that per unit length it remains same. Let's think of a little more in more detail. The gas molecule will have some concentration at the liquid gas interface, and what do you think that concentration is going to be? The solubility, let's say it's going to be the solubility of the gas in this liquid. I call it at Ca0. So initially when I think of this Ca0, can you say anything about the diffusive flux in the x direction compared to the diffusive flux in the x direction? Which one is going to be more? The diffusive flux in the x direction. Will it be same? If you are right, then the diffusive flux in both cases should be the same, but would it be same? Why not? If no, why not? Think about it. You start with 0 concentration of the gas at the top, but when you are, let's say, at this point, this liquid has already some gas molecules in it, distributed inside it. So when you come to this point, the gradient, the driving force is going to be slightly less. So less amount of gas is going to get absorbed for per unit length as I move in down to NZ. So your rate of gas absorption will decrease as I move in this direction. Okay. So you have to decide which length you are going to provide, because after a certain distance, this length becomes unimportant. I mean, this rate is going to get progressively slower and slower, lower and lower. So less amount of gas will be absorbed by the liquid. Does that answer your question?
Diagram also said it will be reversed. So 4 molecules and 3 molecules.
All right. Okay. That should be reversed. So we understand that the gradient for diffusive flow of the gas in the plus x direction will change as I move in z. Now what would happen? Suppose what would happen if the flow rate, if this liquid which is flowing, does it have a distribution in velocity? Will it have a distribution in velocity? Forget about mass transfer now. Let's say we are talking about fluid flow only. The liquid film which is falling, will it have a distribution in velocity with respect to x? Okay. And what kind of velocity distribution you are going to get? Whatever it, where is it going to be maximum? Maybe at some point here, as I move in this, it will slowly go to 0. Okay. Now I would like you to think about this section in slightly more detail, This is the profile that you are going to get. Okay. So if it's a parabola, it will probably look something like this: maximum velocity V max at this location and velocity equal to 0 at this point. Keep this in mind for future discussion. Okay. This we will come back and discuss again. Now, if you have to make a mass balance, what is going to be your control volume? I know that you are now equipped with the equation for binary diffusion, diffusion in binary systems. But if you have to use, let's say, a mass balance, you first have to define a control volume, and that control volume should have del x, del y, del z, something like that, maybe del x only. How do you define the control volume for deriving the governing equation? What is going to be the small dimension? Delta z or delta x? It should be both, because your concentration is going to vary with x and it's going to vary with z as well. All right. So your control volume should be of delta x and delta z, and then we are going to make the balance of mass coming into such a control volume. So how do I draw such a control volume? You can yourself see that it's becoming slightly difficult to visualize a system. We should rather use the equation directly. So just to give you some idea how we are going to devise such delta x and delta z. So this is my delta x, and this is going to be my delta z. I am sorry, it is the opposite, delta z and delta x. So, this region is going to be of interest to me. That is the differential control volume, which is delta x, delta z, and of width w, which is essentially y. Okay. This w is a constant. So, that would be the area through which mass is entering the control volume and leaving. And we define the mass flux, the components of mass flux, the non-zero components of mass flux are NaX and Naz. So, NaX and Naz are the components of mass flux. So, NaX means it is going in this direction, Naz means it is going in this direction for the system we are dealing with. Now, if you write this equation, if you write the in and out in the x direction, which is the area that it is going to encounter for the flux in Ax, which is the area? Delta z times w. Okay. The Naz is going to encounter an area of delta x and w. All right. So, you have four terms Nax multiplied by w times delta z evaluated at x minus Nax w times delta z evaluated at x plus delta x, Naz multiplied by delta x w evaluated at z minus everything evaluated at z plus delta z. There is no reaction term the gas A, which is getting dissolved into liquid B. These two are non-reacting system. So, if it is a non-reacting system, mass in minus mass out, considering all the two directions, there is no reaction, it is a steady state. So, the sum of that would be equal to 0. All right. So, no reaction term and its steady state. So, no change in concentration of A at a fixed location with time. So, the accumulation part, the right hand side of that equation is also 0. Divide both sides by w times del x and del z. Take in the limit, what you are going to get is del x del z of Naz plus del x of Nax is equal to 0. This is your governing equation. Can you visualize the system? How we are doing it? Is there any problem? The same exercise you can do by simply writing the diffusion equation which we have derived in the last class. The equation that one can use, what we have developed in our last class, is del Ca del T plus del Nax del x plus del Nay del y plus the z term is equal to Ra, where this is the amount consumed by reaction, etc. So, how do you get the governing equation? Steady state, first term 0, no reaction, no consumption of A, no conversion of A into anything else. So, this is going to be 0. So, what you will be left with is del Nax del x and del Naz del z equal to 0. So, this expression for which you have to do a thought experiment and find out what is your area of interest can simply be obtained by writing the equation, cancelling the terms which are not there, and you get back the same thing. So, that is the use of writing starting with a general equation and cancelling the terms which are not relevant. Okay. So, this exercise is just to show the utility of starting with a general approach. All right. So, we know that this is going to be my governing equation. Now, this governing equation, in this governing equation I have to substitute Naz and Nax. All right. So, let us start with Nax. This is going to be minus dAb del Ca del x, that is the diffusive term, plus x a times n a x plus n b x. This we have seen many times before. Anything that I can neglect? Is it going to be only nbx or something else? Which mechanism of mass transfer? Okay. This portion refers to bulk flow, and we do not have any bulk flow in the x direction, and it's very sparingly soluble. So obviously the movement of A is also not going to produce any bulk flow. So this term would be equal to 0. So I only have diffusive transport of A in the x direction. So when I write the same thing for Z, which term I am going to keep in there? Only the bulk flow term. The diffusion is going to be relatively unimportant. So if I write NAZ, it's simply going to be XA times NAZ plus NBZ, and this can be approximated as CA times VZ. This VZ is a function of x. Okay. NAZ plus NVZ is equal to CV. This the relation that I have used is NAZ plus NBZ is total concentration multiplied by the velocity in the z direction. So this multiplied by XA would simply give me CA times VZ. That's a relation which I have used. And we also understand that this Vz is a function of x. All right, Vz will change depending on where we are. So when I put these, is there any question about the simplification of the expressions in NAZ and NAX? One is predominantly bulk flow, the second is predominantly diffusive flow. That's the only condition. Those are the two conditions which I have put on the system, and I am supported by the fact that A is sparingly soluble in B. So if that's the case, then I can go back to my governing equation and substitute the expressions, the simplified expressions for NAX and NB and NAZ. The relation that one would get is Vz del Ca del Z is equal to DAB del 2 Ca del x square. This is the governing equation which one has to solve in order to find the concentration profile of A in the falling film as a function of x, z, DAB and the velocity with which the film is coming down. Before I integrate this, I have to do something about Vz. Vz is not a constant. Vz varies with x. In what kind of variation we have for Vz? This part we have already solved previously in our fluid mechanics part of the problem. So that would simply be Vmax times 1 minus x by delta, where delta is the film thickness. The rest will remain unchanged, and once I have it in this way, this Vmax is a constant. It does not depend on x or z. So right now I have an equation in which the dependent variable C A is a function of the two independent variables x and z and some other parameters present in the system. This Vmax you probably do not remember, but you would still be able to tell me would depend on certain things, and we should clarify at this point what is the limitation of the present exercise. Would you be able to tell me on which factors this Vmax would depend on? Conceptually, not expression, conceptually. Viscosity. So viscosity is, it's going to depend on viscosity. It's going to depend on what is the body force field that we have. So that's a constant gravity here. It would also depend on rho. So this is going to be rho and some other things. When I express it in this form and integrate it, what am I assuming? if I could integrate this equation, if I viscosity Vmax is constant, so that means the viscosity and densities of the liquid are remaining constant. And can I justify that? Because I know that viscosity is not I mean the density is not a strong function of other things, okay, but viscosity is. Okay. So, my sparingly soluble comes in here as well. So, when I am saying sparingly soluble, I am assuming that my viscosity will remain unchanged with Z. That means, as we go along the falling film, even the more and more A is going to be absorbed by the liquid, it is not going to significantly change viscosity. Later on, you may come across situations in which viscosity is going to be a function of concentration, and in that case, that concentration dependence of viscosity will make the mass transfer and fluid flow problem coupled. You won't be able to solve any one of them independently. Right now, you can independently solve the hydrodynamics part, the fluid flow part, because all physical properties are independent of concentration. But suppose if this is a function of concentration, Vmax is a function of mu and mu is a function of concentration, then without solving this equation, you won't be able to find Vmax. Without finding Vmax, you won't be able to solve the mass transfer part of the problem. So, that is what a coupled process is. But here we are assuming that these two processes are uncoupled by the independence by the constant value of mu. Okay. So, this is for more complex problems which you may encounter in future. All right. So, right now we have this situation which we would like to solve. Now, how many conditions on Z I would want and how many conditions on X I would like to have? Two conditions on X and one condition on Z. What is the condition on Z that we are going to see A, which is a function of X and Y? What is I am sorry X and Z? What is the okay? So, C A at any X Z equal to 0 is going to be 0. That means the liquid starts as a pure liquid at the top. So, this is one what we can use. And what are the two conditions that we can put on X? One more time, please. Okay. So, at X equal to delta, del C A del X is going to be equal to 0. Do you agree with that? What does this say about the wall? Okay. It's impermeable to the diffusing gas molecules. Gas molecules will not diffuse through the solid wall. So, that's one condition. And the second condition, Ca is equal to 0. At Ca is the solubility of gas. So, let's call it a constant Ca0. So, these are the three constants one will have to use to solve the problem. Now, this in itself is difficult to solve analytically. Okay. You may have to resort to numerical integration. All right. So, we are not going to go into that numerical part in this. Rather, since this being a course, we would always like to have a nice analytical expression which we can use with ease. So, in order to obtain an analytic solution, what we are going to do is we are going to solve this problem under a very special condition, which is also known as a limiting form of the solution. So, the solution that we are going to get is going to be valid only at very special situation, which is the limiting form. And the limiting form, what we are going to do, say is that A, this is the limiting solution. That A penetrates only a small distance in the liquid. Remember, our equation is Vmax this is my governing equation, and the extra condition which I have put is this one. that A penetrates only a small distance in the liquid. Would you be able to tell me what is going to be the advantage of making this assumption? A penetrates only a small distance in the liquid. You remember the velocity profile which I have drawn over here? This is the velocity profile. Okay. If this is the velocity profile, and if we know that the molecules are only penetrating a small distance in the liquid, okay. So when you say x by delta is small, is it x by delta small or delta small? X is a variable, so it can have any value. What about delta? Delta is the liquid film is of thickness delta. All right. So delta you are not changing. What you are saying is the penetration of the gas molecules inside the liquid is rather small. So that means the penetration depth of is small. So if the penetration depth is small, then the absorbed gas molecules, which velocity with which they will travel? Is that clear? The profile of the velocity is like this, parabola. So if the penetration depth is rather small, then all absorbed gas molecules can be approximated to travel with a velocity equal to this one, which is V max. All right. Is that part clear? This assumption makes us use a constant value of velocity. The problem that we are having before is that the velocity is also a function of x, but what we are doing right now is, since the penetration depth is small, all molecules, gas molecules, can be approximated to travel with a velocity equal to V max. So I get rid of this part, and my new governing equation is going to be V max del Ca del Z is equal to dAb, and the rest of the things remain unchanged. Conditions. So this is the change in governing condition which I could achieve, and let's see what's the can I simplify, change any of my boundary conditions for this specific problem. Z equal to 0, Ca equal to 0. No change. This is as simple as possible. There can be no more simplifications. At x equal to 0, so this is the first condition on Z, this is the first condition on x. At x equal to 0, Ca is a constant, Ca 0, and the second condition on x is at x, it was at x equal to delta, del Ca del x was equal to 0. Now I am going to write this as x tends to infinity, what is the value of Ca? Now what is infinity in this case? Infinity we define based on our convenience sometimes. This is the outer edge of the falling liquid film. The gas has penetrated only a small distance. This is delta, which is fixed. This could be centimeter or so, but the diffusing gas molecules will form a boundary layer. What we are saying is that the thickness of the boundary layer is small. So any point outside the boundary layer, what is the concentration of A? 0. Is that clear? So if I go beyond this layer, which we have ourselves said that it is very thin, so if I go beyond that, the Ca has to be equal to 0. So for any value of x greater than this whatever be this, if I denote it by delta 1, if x is greater than delta 1, my Ca should be equal to 0. What I am doing for mathematical convenience is I am writing x, when x tends to infinity, Ca is equal to 0, which is equally valid. If it is 0 here, it is 0 here, it would be 0 at infinity. and this delta can be considered as infinitely thick compared to the thickness of the film delta 1.
So the film should be like this.
The film that I have drawn here, you are talking about this film. The film that I have drawn here is it marks the extent inside the liquid where A molecules are present. So, A molecules are not present at z equal to 0. So, the thickness of that film delta 1 is 0 at x or z at z equal to 0. As I move down, A molecules will get dissolved, A molecule will diffuse. So, the thickness of that imaginary film will increase. As I move down even more, the thickness will slightly increase. So A molecules are there only in only inside. So, that thickness should increase with Z.
So, but we have also concluded that the A molecules will diffuse less as we go down.
Agreed. A molecules will diffuse less. That doesn't mean, so that means the rate of growth of this layer will decrease with Z, but it will still increase. Yes.
And this assumption will be valid that the penetration layer is not
Right. Okay. His question is, when is this assumption going to be valid that the penetration depth is small? Now, there are two ways to answer it. One is when you are from an operational point of view. When you think you are operating the system in such a way that you are making the penetration depth small. So, how do you do that? How, as an engineer, you would make the penetration depth smaller? High velocity. And what is more high velocity or short length? High velocity, high value of the velocity with which the liquid is coming down, or short length. If you combine the two, what do you get? Small. Velocity is meter per second. Okay. Length is meter. How do you combine it to get it something more scientific? Velocity has units meter per second, length has a unit meter. Can you combine it to give it a more meaningful expression instead of saying velocity should be more, length should be short? Contact time. Okay. So, the contact time should be less. So, from an operational point of view, this assumption is valid when the contact time between the gas and the liquid is small. Okay. So, the velocity should be more, length should be less, or in other words the contact time should be small. If I think of from the property side, this assumption is going to be valid when if I look at property side, from the property of the gas and the liquid, when this assumption is going to be valid. Look at the equation and tell me, this penetration depth, on which property would it depend on? D means the diffusivity. Okay. So, as the diffusivity is more, would you expect the thickness to be more or less? So, the penetration would be more. If you have, so diffusivity definitely will play some role into this. Now, we are talking about probably two diffusivities here. One is mass diffusivity, which forces the A molecules to move in this direction. And suppose if this liquid is coming down, if I keeping everything constant, keeping the gas constant, suppose keeping the diffusivity constant, I change the liquid and make it a high viscous liquid, what is going to happen to this penetration depth? If the viscosity is high, what is going to happen to the diffusing molecules? If the viscosity is high, then do you think that it would be easy to move in this direction or difficult? If it is viscous, you are putting your finger across a falling film of water and a falling film of molten soap. Obviously, you have to, it is going to be difficult for the case of molten soap. So, if it is viscous, then definitely you are going to have less thickness of this one. And when I talk about viscosity, density, etc., what number I am referring to? What kind of diffusivity I am referring to? its viscosity and density taken together. No, viscosity and density taken together. What is mu by rho? Kinematic viscosity. The more correct name for this is momentum diffusivity. Okay. Momentum diffusivity. You have definitely come across this. If you work out the units, you'd see it has the same unit as mass diffusivity. So you do have two different types of diffusivity. One is in fact three diffusivities: momentum diffusivity, mass diffusivity, and what is thermal diffusivity? What should be in the what should be always look at analogy. What should be in the numerator of thermal diffusivity? If it is mu, it has to be K, all right, K by rho Cp. This is the thermal diffusivity. So you have three diffusivities: momentum, mass, and thermal. Now, if so, I know that my thickness of that falling film is going to depend on these two. And as I mentioned to you, these two have same units. This is also meter per second, this is also meter per second. So, if these two have same units, then shouldn't a dimensionless group automatically generate from these two? This has the same unit as this d. So, how do I make it a dimensionless number? Divide this by this. So, that is how the dimensionless number mu by rho d, which is Schmidt number, MIDT, okay, fine, Schmidt number, which simply tells you the ease with which you can have momentum transfer, I mean the ratio of momentum diffusivity to mass diffusivity. And Schmidt number is large for oils, etc. Schmidt number is small for glycerin, water, etc., these kind of fluids. So, the thickness of this layer would depend on what is the Schmidt number of this liquid which we are dealing with, as of the liquid and the gas combination. All right. So, if we look back at our the basics are clear. Mathematics, you can look at your textbook and you can follow. There is nothing in the mathematics, but we should at every point we should know the physical implication, physical significance of the process. So, motion in this direction is going to be enhanced by high diffusivity, it is going to be retarded by high viscosity. Okay, these two are at opposite purpose. So, I am going to solve this equation, and what is the solution of this? The last problem we have, the problem that we have done in the last class. If you look at the solution, it is going to be error function again. Okay. I do not know if it is the last class or last to last class. It's a classic case of error function. For all, again I am reiterating that whenever you come across any such situation for which standard solutions are available, I do not want you to solve, to show the steps. Write the governing equation, write the boundary conditions, and immediately write the solution by looking at any text. Okay. So, this is z and this is x square, all right, or the other way around, whatever you can find out from this, find out from your previous, whenever I have written del 2 Ca del x square. So, if it is error function solution, the solution would be, I am directly writing the solution as Ca by Ca naught 1 minus error function x by now error function, if I call this as eta, this whole thing as eta, it is 1 minus error function of eta. I am not sure if you know about how error function behaves. If the value of eta is known, what would be the corresponding value of error function? Do you know that or not? No. Okay. So, just give you it's available in tabular form in any book. This is for error function eta and error function. So, if it is 0, error function is also 0. If it is 0.1, this is 0.112. If it is 0.5, this is also about 0.5. And when this in this way, when it goes to 3, this is about 0.999498, and if it's 2, it's 3 nines. So, if this is known to you, this table is with you, can you somehow use this table to define what's your boundary layer thickness? Can you do that? If I tell you that at a specific z location, find out what is the boundary layer thickness. That means up to which point your gas molecules have penetrated the liquid. What you are going to do? Simply put this equal to 3, eta equal to 3. You know Z, you know Vmax, you know DAB. Find out what is going to be your boundary layer thickness at that point, because your boundary layer thickness is nothing but delta, I mean x at which error Ca is almost equal to 0. So, when this is equal to 3, Ca is almost equal to 0. So, put this value to be equal to 3, find out what is the thickness of the penetrating, what is up to which extent you are going to find some A in the liquid film. All right. So, that is the beauty of error function, that after a value of 3 it remains almost unchanged, it is almost 1. So, it gives you an idea of what is the penetration depth of A molecules in the liquid. Okay. So, once this form is evaluated, you can do some more exercises. For example, if I like to find out what is the local mass flux at this surface. At this surface means at x equal to 0. So, how do you find out the local mass flux of A molecules at x equal to 0? This is my figure again. You already know Ca by Ca0 as a function of several other things. So, how do you find out the local mass flux? Del Ca by del x evaluated at x equal to 0 multiplied with minus dAb. This is what you are saying. So, the local mass flux at x equal to 0 would simply be equal to minus dAb del Ca del x at x equal to 0. All right. And in the last class itself, I have given you what is going to be the error function del x of that error function evaluated at x equal to 0. So, if you do that, fine. What you are going to get, maybe I can write this thing again one more time for your benefit. So, if I do it in that way, NaX so I can evaluate NaX, which is the movement of the absorption of the gas molecules at x equal to 0, and I also realize, as we have discussed before, this NaX is going to be a function of Z. Is that clear? As we have discussed, as I am going to have more and more A molecules present towards the lower portion of the film, the amount of absorption of the gas will be reduced, because I am simply making this as a control surface. Whatever motion of A molecules I have up to this point at steady state has to be diffused into the liquid film. So, this is my control surface. On this side, I probably have some HM times C A infinity minus C at the interface, which is C A 0. This should be equal to minus D times del C A del x evaluated at x equal to 0. So, I am evaluating this part to find out what is N A Z. Now, as we have seen, with increase in Z, the value of N A, would it increase or decrease? Do not look at the expression, think physically and tell me. As Z increases, as I move towards the lower portion of the film, should my flux increase or decrease? Should decrease, and you see that is supported by the expression that Z is in the denominator. So, this is mathematically why NAZ should be NAX should decrease with Z, but fundamentally it should be very clear to you why NAX decreases with increase in Z. Once this is known, then you should also be able to calculate what is the total uptake of A molecules by the falling film. This is at any Z location, but I am not only interested in any Z location, I would like to find out what is the total uptake, total amount of A absorbed by the film. Okay, so, in order to find out the total amount, you integrate this from 0 to whatever be the final value of Z, which is L, multiply it with W. Okay. So, integration of NAX at x equal to 0, it should be integrated from 0 to L, and it has to be dz, and it has to be multiplied by whatever be the width of the film. So, that would give you the total uptake of A molecules by the falling film of liquid. So, what we have in summary, what we have done in this class is we have seen a problem which is a coupled problem, a fluid flow problem coupled with mass transfer. We could decouple these two by making an assumption that viscosity etc., these properties are not going to be altered, not going to depend on the presence of A molecules in the system, which would be true if A is sparingly soluble in B. Then we have seen that what the diffusive flow in x direction predominates, whereas the bulk flow in the z direction predominates. So, starting with our basic equation for mass transfer, I could write the governing equation and substituting the expression for V, Vz in terms of Vmax, x etc., and I can find out what is going to be the total governing equation, which can only be solved numerically. So, I am looking for a limiting solution, and the limiting solution is when the penetration depth of A molecules is small. So, if A molecules do not penetrate into the film to a large extent, then it can be assumed all A molecules travel with the same velocity, which is Vmax, which makes our problem simpler, our equation simpler. And we also understand that after a certain distance, no A molecules are present in B, since the penetration depth is small. So, I could reformulate my boundary conditions in such a way that a standard solution can be obtained, and we found the standard solution to be error function solution. And we also see that depending the nature of the error function gives us a way to demarcate, to find out up to which extent, what is the thickness of that penetration depth. And once we have the functional form of concentration, I could use that to find out what is the absorption at x equal to 0 at the liquid gas interface, and we understand that it is a function of Z. So, once we find out the expression for absorption of the gas at any x, I could integrate it over the whole length of the film to find out the total uptake by the falling liquid in contact with the gas. Is there any question? Yes.
So, what will happen at Z equal to 0?
Okay.
Surface flux tends to be infinity according to the
All right. Yes. That is a very interesting question. What is going to happen to the thickness to all other parameters at Z equal to 0? Because you would see that in many of the expressions, not only for thickness etc., Z comes in the denominator. So, can I put a value of Z equal to 0 in there? Obviously, I cannot. So, what is done for solution of these cases? That's a very valid and very good question. What is done in those cases is an asymptotic solution is sought for a small value of Z. Okay. You know about asymptotic solution? Probably you have heard about it. So, the governing equation for very small z is sought, and that how do you decide about the small value of z? What is small? Is 0.1 centimeter small or is 0.001 centimeter small? So, in order to find an asymptotic solution, what is done is ultimately your final result should not depend on whatever small value you have chosen for your asymptotic solution. So, the solution that we have obtained is not valid at z equal to 0. An asymptotic solution, that means a solution which is valid only for very small z, is used, and what is very small is calculated, is determined by repeatedly solving the problem and seeing the dependence of the final result on your assumption of that z. When it becomes independent, that is your correct asymptotic solution. So, we will give you more examples of asymptotic solution in the second part of this course, but that is how roughly it is done. Thank you.
Well, good morning everyone. So, we will just take up whatever we have left in the last class. In the last class we were discussing about the similarity solution, and we have seen that there are several transient as well as two dimensional steady state problems can be solved using similarity solution. Now, we have discussed about the criterion of having similarity solution of a particular differential equation, and the thumb rules we have found out that the nature of the equation has to be parabolic. That is one condition. The other condition is that one of the boundary condition must be residing at infinity. If these two conditions are met, then you may be having a similarity solution of the governing equation. So, we have solved the Stokes' first problem to illustrate how to use similarity solution, how to obtain the similarity parameters, so on and so forth. So, we have started in fact discussing a second example, that will be the basically a growing concentration boundary layer over a porous ball. It may be a membrane surface. So, we will continue the discussion and get the complete solution today. So, the problem we are discussing about let us look into the system. You are having a rectangular channel, a channel with a rectangular cross section. Okay. Cross section, and it is a very thin channel, that means the height is very small. Now, our y axis is from the bottom surface facing the top, and this is x axis. The length of the channel is x equal to 0 and x equal to L. Now, half height of the channel is small h is the half height, full height is twice h. Now, we are you are placing a porous surface at the porous the bottom plate is basically porous.